and you'd be able to finish easily. Okay, so a graph's going to look like this, okay? And after, thought about it a little bit, it's fairly easy to do these graphs. For the A versus X, when X is over here, which corresponds to this point on the X-axis, A is positive and as big as it's going to be. So we just put a point down here. There's your A. Okay? That point's easy, right? And there are other easy points. This point's easy, right? A is 0, so we got a point here. And then over here, A is in the opposite direction, but it's like here. So it's perfectly plausible that your graph is a straight line. Okay? Now if you put the intermediate points in, well, A is a little less here than it is here, so that would correspond to a point in the straight line, and that's what y'all have conjectured. But of course we're just dealing with pictures that I drew. Not particularly accurately, but try to be representative. Okay? Reasonable accuracy, but you're not going to establish whether this is a straight line based on my picture. Okay? So we're going to use the fact that if the net force is negative kx, then we know that x of t is a cosine of omega t plus a phi. But I'm claiming that phi is pi radians, okay? And how do I claim that? Well, if actually okay, we'll see in a minute. Depends on how you graph your function. Okay. Somehow I had second thoughts about that, but I'm right. Okay, so V versus T is going to be a little different. Your velocity is going to be always positive going this way. So your velocity is going to start, well, it's 0 or positive. It's going to start at 0 because presumably this is where the pendulum is stationary. And then it's going to take a pretty big jump between here and here, okay? And, well, let's say here's its maximum. Its maximum occurs at 0, so we know we're going to have a point here, okay? Now, I don't think this is a straight line. This is a big jump. This is a smaller jump. This is a smaller jump, right? So you got a big jump here. You get a good bit of your velocity here, you get most of the rest of it here, and only a small change here. Okay? So it's going to be like this. If you accept that the acceleration is decreasing, so your changes in velocity are decreasing. And we'll relate that to other characteristics of the graph here in a minute. But so, not drawing this graph with any kind of this point should be a little further over. Okay, so it's going to be an arc of some kind. Maybe it'll be an arc of a sine curve. Maybe it'll be a semicircle. Maybe it'll be parabolic. Maybe it'll be something completely different. There are lots of different kinds of arcs. Maybe it'll be an inverted catenary. Okay? No, but you don't know at this point. Okay, you don't know until you do a little analysis on it. Okay? Now, the physics is this picture. Okay? The physics is really represented by this picture because the accelerations follow the tensions. The tensions are what you get here. And we haven't done the trigonometry of the picture yet. We're just getting the picture. Once you have the picture, if your math is in decent shape, that's easy. Understanding what's going on, that's what's hard. Okay? So instead of starting with these things, and of course, a week ago we derived all this. Okay? And that was just pure math. Once you have the assumption here. Now the assumption is physics. Then you do some math, then you relate it to reality here, or to what you expect reality to be based on your assumptions, and represent it by picture, okay? It's really a big deal. If you learn nothing else in this course, it's how to picture things, how to represent them on graphs, and then how to do the analysis, which we're going to do here in a minute, okay? And you'll find that the analysis is really simple if you understand sine and cosine functions. You can take a couple of simple derivatives, okay? Okay, so anyhow, we've got this. Now, acceleration versus velocity, I'm going to ask you to do that yourself, and I'm going to ask you to do it by analysis for homework, okay? It's not an unimportant graph. It's not as directly related to the physics, and the nature of the graph is very interesting, okay? Okay, so, it's just good for your soul to do this graph. And it does help understand more abstract representations in physics. It's a little more abstract than these, okay? Okay, well, anyhow, okay, we know that with this assumption, we get this. And actually, the arrow goes both ways. This is an implication. This follows from this, and this follows from this. Okay? And easily proved that if this is true, this has to be true, if you accept Newton's second law. No reason you should just because I said so, or just because you've heard it before. But in Lab Friday, we'll do at least a couple experiments. Tend to confirm Newton's second law. Okay, so anyhow. Okay, so what's V? What's your V of t function? Well, how's velocity related to position? What's the definition of velocity?
It's the rate of change of...
It's the rate of change of your position with respect to time. Good.
Meaning it is also its derivative.
I'm sorry?
Meaning it's also its derivative.
Well, yeah, the rate of change is derivative, and of course, what is the rate of change of this function? It's its derivative, right? But the definition is not derivative, the definition is rate of change. That's a concept you need to have, because the derivative is just a mechanical process. Okay? That's not physics, that's a mechanical process. Okay? Okay, so anyhow, you take this derivative, you get negative omega A sine of omega t plus phi. And then you take the derivative of that to get the acceleration, because acceleration is the rate of change of velocity with respect to time. And you've always, anytime I ask you what the definition of velocity or acceleration is, that's your answer. Not the derivative of, it's not some fuzzy concept, although you want to have fuzzy concepts to make specific here, okay? So you get negative omega squared A cosine of omega t plus pi. Okay? Well, how is A of t related to x of t? We're looking at the A versus x graph, right? Well, here's the expression for A of t, here's the expression for x of t. What do you see? How are they related?
A of t is just x of t multiplied by negative omega squared.
Yeah. So A of t is negative omega squared x of t. So this graph should be a straight line through the origin with slope negative omega squared. Make sense? I mean, it has to be, you know, y equals mx is, you know, m's a slope, and you don't have any b on it, so the intercept is 0. And that should be totally familiar to you. That's one of the most important functions there is. Just plain old y equals mx, because that's one of these. And this mimics this, actually, and you might think if there's any deep relationship. And mathematically, clearly there is. Yeah, but whether you do or not, understand this. This explains why this graph is a straight line. Okay? Now, a little more complicated. How are V and X related? Well, you've got a sine here and you've got a cosine here, right?
V of t is the negative omega inverse of x.
Inverse of X? Well, kind of, not really though. Well, what you have to understand is, when you see a sine and a cosine being compared, what's the Pythagorean identity for sines and cosines? Again, something else you're going to use again, 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 and then you're going to start using it a lot.
Fair enough.
Okay? So it's fundamental. It's always got to be right there in front of your mind. You've used it. Sine squared of something plus cosine squared is the same thing as 1, right? Okay? So we got to get a little more tricky. Instead of just observing that this is a negative constant multiple of this, so you do expect a negative straight line, you know, a decreasing straight line through the origin. Okay? Okay, so, well, okay. You've got a sine and a cosine of the same thing. You've got to be very familiar with that. If you did any integration in your calculus course, you used that a lot. Okay? If you didn't use that a lot, you probably ought to go back and do some problems involving trigonometric functions, trigonometric substitutions, and just other basic substitutions, because it comes up very frequently. Okay? Okay, well, now we can't say, you know, we'd be tempted almost to say, okay, so v squared, v is a sine, x is a cosine, so v squared plus x squared equals 1, right? Now that's not really true because you got stuff in front of these. Now if you didn't have the omega here, you could say, okay, v squared plus x squared would be a squared, okay? But you got an omega here, right? So you got to somehow make these constant. Well, it's fairly simple. The cosine of omega t plus pi equals x over a. And I guess I'll put the t in there just to remind us that that's a function of t and it keeps changing. Okay, and the sine of omega t plus pi equals negative v of t over omega squared a. Okay? And then, well, sine squared of omega t plus pi plus cosine squared of omega t plus pi equals 1. So since the sine squared is this, then this squared, and the cosine squared is this, then this squared, when you add these two squares, you're going to get 1. Wasn't a particularly great sentence, but you got the idea. Okay? In other words, this is equal to this is equal to this. Well, this is equal to this, and this is equal to this, so this is the square of this. There it is. And this is the square of this. There it is. Okay? I'm still not sure I pointed right. Still. Okay, well, you can then write this as this. And what's that the equation of?
That's just the distributed version of the previous equation.
The what?
The distributed version of the equation above.
Now that's the equation of a very important and very common shape that you should have studied in pre-calculus, but now it's been moved to calculus near the end of the year. And of course you're not, I'm not sure, your course was not one of our courses. It wasn't a community college system course, it was an AP course. So hopefully you didn't miss it. It's a conic section.
It's what?
It's a conic section. You know what a conic section is? Make yourself a note. First time you have some spare time, learn about conic sections.
Conic like a cone, right?
Yeah, it's ellipses, hyperbolas, parabolas. Okay? You can't come out of a mathematics sequence that ends in calculus and not know conic sections and consider yourself to be fully literate. No offense, you can become fully literate. Okay? But by the end of a calculus course, you should be completely conversant in conic sections. If you're desperate enough, I can give you reference to some videos that I did, but you find videos all over the internet, so you're probably better off there. Okay?
I'm fairly certain I've seen it before, I just never heard it called that.
You haven't had it. You'd recognize it. So you got to learn it, but don't try to learn it tomorrow, but hopefully learn it before we get to planetary motion. Okay? Because that's elliptical. Most of the things we're going to do before then are not. Parabolas are conic sections, but you know how to deal with those and just graph your quadratic functions and you can treat them that way. Until, of course, we get to optics second semester when you have to understand the conic sections again, focus, directrix, all that stuff. Okay? So you got to know that, but not today. But since you don't know that, I've just got to say, make yourself a note that this tells you exactly why this is a conic section. This is an ellipse. The semi-axes omega squared A and A. Okay? Meaning, this distance here is omega squared A. This distance here is A, obviously. Okay? Because, why is this distance A? Why is this distance equal to A? Because what's the maximum possible value of x of t?
A times 1 or just A?
A times 1 what?
Or just A.
Okay, yeah, I thought you, A times 1, or just A. You didn't have the comma in there, and I thought you were saying something about A, and I wondered what in the world you were thinking. But now I know, okay? And that's right, totally right. Because the maximum value of the cosine is 1. Cosine goes from -1 to 1, so it goes, well, so x goes from -A to A, right? So clearly, this better be A, right? And then this turns out to be omega squared A. And of course, this means that my graph wasn't very accurate, because this is only half of an ellipse that goes down here. And the ellipse, in order to be an ellipse, it's just a distorted circle, has to be vertical right here. So I should have, you know, my graph should come vertical, okay? I didn't draw it that way because I didn't want to use any previous knowledge, okay? You probably would have drawn it this way too. Now, if you had very accurate calculations for these things, okay, then your graph would very plausibly be elliptical. So I can kind of correct this graph a little bit. I don't have another good color, but it does this. Just has to change a little bit so it becomes vertical at these points. And then it also completes the ellipse, because of course when you start here, if you, as I will ask you to do for homework, draw the vectors for the return from here back to here, you're going to find that the graph does this, and that that's consistent with what the analysis tells us. Okay?